Hey guys, welcome to this lesson. This one we're going to jump right into. It's called Polynomials. And it's an introduction on polynomials. We're going to be spending some time with those in the next few lessons and getting hands-on with them. So, polynomial, that comes from the prefix poly, which means many. If you are into polyamority, it means you have many partners. If you're polytheistic, you believe in many gods. And polygamy means many marriages. Okay? Nomial is the suffix here. That probably comes from the Latin nomen, which is name, because polynomial means many terms. So a polynomial is made out of these guys, which is monomials, and that means one term. So a polynomial is made out of many terms. Okay? In a monomial, it's pretty simple. It's a product of constants and or variables. So 3x is an example, or x squared, or 2x squared y cubed. Okay, those are all random examples of monomials. Polynomials, we're just putting them together because a polynomial is a sum of monomials. Now don't get scared if you see subtraction in polynomials. That's ordinary. If you subtract 3, that's the same thing as adding -3. It's still a sum of something. It's just a sum of the negative thing. But don't let that get you hung up. You're going to see addition and subtraction in polynomials. That's totally normal. So, what are these made out of, though? Right? So, a polynomial, it's made out of terms. And each of those terms has coefficients and it has a degree. Right? Oh, it's done such a great job in life. It's got what I want. It's got a degree. So, they have coefficients and they have degrees. Let's look at what that means. I hope that you can see the whiteboard here. In fact, I'm not even going to risk it. Let's just switch right over to the tablet, okay? So I'm moving over to the whiteboard. I'm down here in the corner. You can still see me. All right. So here we go. I've written an example up here of a polynomial. Now this guy, he's in a bit of disarray, right? It's out of order, and I'm going to show you why. But for right now, let's look at what coefficients are. Coefficients are what your variables are being multiplied by. So here's a term, here's a term, here's a term, here's a term, and here's a term. Your coefficients are what your variables are being multiplied by. In this case here, this 4. In this case here, this 3. This 2. And there's an invisible -1 in front of that x, you can think, because it's minus x. So minus 1 times x. So there's a hidden 1 coefficient right there. And you know that from working with variables, that 1 times x is x. So now, the most important thing about a polynomial is its degree, right? So by degree, I mean, what is the exponent here? Well, with this 4x, just the plain 4x, the exponent is a hidden 1, right? But it's not written. Your exponent here in this term is this 3, because that term's being cubed, or that x is being cubed, and then multiplied by 3. This -2x squared, the degree is right there. It's that power of 2, okay? So when you're working with a polynomial, what you want to do is you want to rewrite it, if it's not already, and you want to put it in descending order, okay, of the degree. The highest degree comes first. It doesn't matter what these coefficients are. It matters what the degree is. So what's the highest degree with this one, you guys? It's this 3x cubed, because the exponent is a 3, and it's the highest exponent that we have. The next one up is this -2x squared. So write him in next. The next one is going to be these plain x's. We have two of them, actually. So we have a 4x and a negative x. Well, let's just simplify this right here. We don't need another term. What's 4x minus x? It's 3x. So you're going to write in a positive 3x. And then our last term is just a constant. And a constant is really important in a lot of mathematical formulas because it determines what the starting condition is, okay? So plus 1. That's the last term right there. 3x squared minus 2, or 3x cubed minus 2x squared plus 3x plus 1 is our equation. And this guy happens to be a cubic, okay? He is a cubic equation. And those act a certain way. So, what do I mean? What do I mean by act? How can an equation act like anything? Well, let me tell you. And this is where it gets cool. If I'm dribbling a bit, you know what? I'm gonna find a basketball. Hold on. Oh, screw it. I don't know where it is, but I'm gonna get. Here's what we have. All right, guys. So, got a ball here, okay? Let's say I propel it into the air, like up, like I'm shooting a basketball. Now, due to the trajectory I let it go at, and the velocity I let it go at, and the Earth's gravity, it's moving in a predictable way. It's moving in a parabola. Up at first, and then sharp, steep down. Like an arch, right? When you shoot a basketball, it's like an arch. It should be, if you're shooting it properly. So that's how a parabola moves, and those are defined by polynomials. Polynomials specifically with degree 2, okay? That's a quadratic equation. So, let's switch over. I've got Desmos open, and I want you guys to see exactly what that means, like on a graph. So let's get rid of this linear here real quick. What we're left with is the simplest quadratic equation, which is x squared. You can see here that the leading degree is 2. X squared makes that exact situation I'm telling you about, which is a parabola. It's a U shape, an arch. In fact, if I make a negative instead, negative x squared, then it's moving in exactly the way I told you a basketball would move. Maybe a bit exaggerated, but the same way. Like an arch, like a hoop. Okay? And we're going to work on these more and more. And you're going to see how these stand out from linear equations, which are probably the simplest, the ones that you've learned before. Like this, f of x equals x. It's a smooth and steady ramp. Well, we're going to get into things such as that parabola, f of x equals x squared, and we're even going to see what cubic functions can do, because those behave entirely different. You can see here that a cubic comes up from these negative numbers, and that's of course depending on the equation you write, but they all are shaped the same way, right? So they come up and they level out and they shoot right back up again. And each of these equations, the domain of the equation is going to be all real numbers. The domain is the set of x values that you can give the function. And we talked about that. What can't a function take? Well, a function cannot return two different values. So when you want the square root of something, that's an example. Or if you want the square root of a negative number, it's just undefined. Or if you're dividing by x and x happens to be 0, that's undefined. But you're going to love these quadratics, these linears, these cubics, all of these polynomial functions, because the domain is all real numbers, negative infinity to infinity, right? They're always going to have a y value associated with them. So I want to keep this lesson shorter today. I want the format to be shorter. So we're just going to look at one problem, and it's going to deal with area of a house, right? So instead of Desmos, let's switch over. Let's get our whiteboard back. I'm going to erase this whole thing here, and we're going to start a problem. So let's start by, let's start by drawing a really strange house, okay? Make kind of a cube shape here. And here's how I'm going to divide this house. It's going to be a room going this way, and a room going that way. We're not going to name our rooms. Really doesn't matter. I'm just talking about area here. You can fill this very stupid looking house with furniture and whatever you want to do. We're just going to define some things here. Does need to be a bit more rectangular. Hold on. So here, let's cut it up this way. And this roughly cube shape, we're gonna give this some dimensions. X by X. Just pretend with me here that this is a cube. This is hard to draw with. So pretend with me here that that is a cube. So our rooms, we have partial dimensions for each of them, right? So there's an X here defining this length, and there's a 3 here defining this length. There's an X here defining this length, and a 4 here defining this length. Well, we can infer because this length is X. Well, this length, you know, there's a perpendicular line intersecting it right there too. So we could say that one's X. This one, you can see the same situation with the 4 down here. So what's the area of this whole thing? We now know each of these shapes, the constituent areas. We should be able to figure it out, right? So this shape here is 3 by X. 3 times X. Well, what's the shape here? This is 4 by 3. Well, we can just do the math. That's 12. This one, this cube shape, is X by X. So that's X squared. And this one here is X times 4, which is 4X. So by putting all these together, and by knowing what X is, and putting them in order, we have X squared, we have a 3X, and a 4X. We can just add those together and make it 7X. And then our last term here is 12. So if we knew what X was in this equation, which could be anything, it could be, well, it couldn't be 1 because this 3 is here, and that's, you can see just visually how much larger this X is than that 3, and how much larger it is than this 4. But if we plug in a value for X, then we could know the area of this entire thing, just by knowing its constituent pieces. So that's an idea of kind of geometry and polynomials. And I'm sorry about my drawing, and probably the dimensions don't make any sense. But you can see how I arrived at this being our equation for finding out what that area was. And we're going to do more with this. We're going to be able to see where a ball will land when shot by a basketball player. I know there's astrophysics that parabolas can work with. We're going to see it's in the real world, and it models so many different things. So stay with me for these polynomial lessons. I think you're really going to enjoy them. And again, we have boosted the technology on the show. I've got a microphone that doesn't hiss or scream or screech. So we're getting somewhere. I hope you guys are learning something because I'm having the time of my life. Thank you for being with me.